So my name is Wendell. I'm one of the students. I'm a master's student at Georgia Tech, and I'm one of the co-authors for this paper. And we had the great pleasure to work with Dr. Melody Jackson from the Animal-Centered Computing Lab to work on this project. So this was a course project that we did, and she advised us for I guess for this project to get it going. So Dr. Jackson has been working with the Georgia Tech Canine police for many years, and this project was in part inspired by some of their work. And so here you see a picture of the canine police here and a dog. So fun fact, in Georgia Tech, before the games, the canine team would usually, the bomb squad would go to the stadium and then clear the stadium before the games, just to make sure there's no bombs or anything. So here, so one of the motivations we have here is, I guess pretty much, we know that it's important that we have the canine dogs because the canines have an incredible sense of smell. They're able to, we use them for like search and rescue missions, such as finding missing people, bomb detection, and like drug searches. But I guess the main thing is that it takes many years for like a handler to be able to understand the subtle cues from the dog. And I kind of personally got an experience of this myself because I recently adopted a dog with my roommate, and we found that it's at least for us, because we're like first-time dog owners, is very difficult to understand what the dog is telling us. Sometimes we think he's just wanting attention, but sometimes, or whether or not he's actually needs to go to the bathroom, or if he just wants to take a walk outside. But in those cases, it's the risks is a little bit less, because the worst case is we'll be standing out like this morning at 3 a.m. Trying to see if he needs to go bathroom. But otherwise, we might wake up with a mess on the floor. But in the real world, like here, the risks are a little bit more high stake. Because we're talking about like search and rescue, and we're talking about like bomb detection and drug detection. But what happens is that often the police and TSA, they only go through maybe like 14 to 18 weeks of training. And so a lot of their training is actually done on the job. So we, as part of this pilot study, we're trying to figure out a way to try and make this a little easier for new handlers to try and understand what their dog is trying to tell them. And part of this is like activity recognition. And here we see that some of the behaviors that maybe an experienced handler would try to notice from the dog when the dog is out on the field and they're trying to search, find the source of the odor. Here's some of the patterns that they might look at. The first one is daisy pedaling. In this case, you can see that there's like an odor cone that comes down. And so odor, generally, I think the odor, the way it moves is a little bit more complicated. And in 3D space, it's a little bit more dynamic than just a cone. But for simplification purposes, it's much easier to try and understand it by just using a cone. And it works as a good general rule of thumb. So you might have a dog and it's trying to, in this case, trace the dot. If you look at the dotted lines, it's trying to trace what looks like a daisy petal. And in this case, what it's doing is it's trying to go around, it's trying to find the edge of the odor cone to try and figure out where the source is coming from. And for daisy pedaling, what happens is that often the source is like at an elevated height. You have a cone that projects down, and the dog, in this case, is doing daisy pedal to try and find the odor cone. You might have other cases where, like in this case, it's called sponging. And in this case, there's like a table, and maybe the odor source is either on the table or maybe it's on it's a little above the table. And so you'll see the dog, it might sponge up on the table and it'll come back down, and maybe it'll move around the table and sponge up, and it's just trying to locate where that source is coming from. So the next one is bracketing. In this case, the dog is sort of like zigzagging, it's trying to find the edge of the cone, and you see how it goes from like a wider cone and wider like travel, and then it goes to zigzags to like a smaller one. It's kind of like, in a way, kind of like, think of like a spiral, but it's not quite that shape. Oh, sorry. No problem there with my touchpad. Okay, there we go. And the last one here we have on this diagram is what we call windshield wipering. And this is sort of like one of the cases that Melody kind of like inspired Melody to sort of like work on this project. Is I think she was at a competition for nosework, and the dog was trying to it was moving back and forth like a windshield wiper, and then so in this case the odor is actually behind the dog, but the dog is sort of like pacing around back and forth in the along this wall. And so Melody thought it was like maybe along this wall, and she called it, and then it turns out it was behind. So the difference between windshield wipering, since it's kind of looks a little bit like the bracketing because you move back and forth, is that in this case it just moves along back and forth in like a line, and then the distance is about equal. With bracketing, it sort of like narrows down. It finds, because it moves towards the cone, and close to the origin is sort of like the cone, the border is a little narrower. So maybe we'll show you, there's one more that we want to show you. It's called head snapping. It's not in this picture, but we have a video for you. So let's take a look at this. Let me pause the video first. Sound, okay. So here you see that you have a canine dog here, and then it's moving along. And at this point, it suddenly changes direction. You can see a very abrupt change in direction. Its head snaps over. That's why it's called head snapping. And then it sponges. Let's play that again so that you can see it again. So it changes direction right around here. That's a head snap. And it sponges onto the table trying to figure out where it is. It looks at top table. It didn't find it, but it found it underneath the table. And then when it found it, it alerts the trainer by, in this case, the dog's behavior is it sits down and it waits for the handler to reward him. That's usually how it's trained, right? You have to reinforce its behavior by giving him a reward. So that was head snap. And so those are the kind of mode patterns that we're trying to, that experienced handlers will try to look for, and that we are trying to, I guess, classify with our sensors. We try to capture the data and then see if those patterns are happening. So for the rest of the presentation, what we're going to talk about is some of the project goals that we had when we were doing this project for the class. And then we'll move on to the type of hardware we used and where we placed the sensors. After that, we'll talk about like the audio data we collected and the model that we trained for Nosework audio classification. And finally, we'll move on to the IMU activity data that we collected and some of the videos. So what we have here, what we called our project was like the sniff pilot study. So that's sensors for Nosework interactive finding for sniff. So the original goal here, what we wanted to do was we wanted to be able to have like a real-time system, like a wearable device we can put on the dog, and then as the handler and the dog is like sniffing, finding, trying to locate the source of the odor, it will classify in real time and transmit that over to maybe like a wearable wearable device or a laptop or something that the handler has, and it'll try and give some information to the handler to understand more of what the dog is doing. And so after that, what we have is we have a labeled Nosework data set, and that was for both audio and the motion, the movement data. And what we have is we have 20 minutes of the labeled data, which doesn't sound like a lot, but considering that each session of those Nosework sessions, I guess, takes about a minute. That's equivalent to about 20 sessions. So then next is we'll talk about like some of the microphones we used. Originally, what we had was like an omnidirectional microphone. Well, the goal of the microphone is that we want to be able to capture the sniffing sounds from the dog, but we want to make sure that any background noise is excluded. So in that case, what we found out was that with the omnidirectional mics, it was we pretty much heard a lot of background noise, like maybe a door closing or sounds from us talking. So that turned out to be, that's not as useful. We found that it was better to just use a directional microphone. So here we have the cardioid pickup pattern, and the pickup pattern for a cardioid is more like it'll pick up sounds from the front of the microphone and a little bit from the sides. So what we did was we pointed the microphone towards the dog's nose so that it would pretty much exclude a lot of the noise from the environment. And that turned out to be both a pretty simple setup and it was pretty effective. We didn't need to do any like a noise cancellation with like 2 microphones or any other complicated setup. It was just put the mic on and then it was pretty good. So in this slide, we have the transmitter that we use. It works on ultra high frequency band, I guess, and it works up to 300 feet. We tested it on the field in the hallways, and it picked up pretty. It was pretty good. Like across the hallway, it was still pretty clear. Only until you start turning around a corner from a far distance, that's when the signal starts to degrade. But in the field, when the handler is following the dog, that's usually not a problem. You have a clear line of sight, and if it's still within a close range, even with some obstacles, it should be fine. So that was for the transmitter. We used 2 of these motions, MetaMotion C sensors, and these are IMU sensors. And what we did was we placed one on the head of the dog and one on the torso of the dog. And so what this allowed us to do was, if the dog was sponging, we would expect the sensor on the head of the dog to elevate a little bit more than the sensor on the back of the dog. So that would give us like some indication of whether or not it's doing like a sponging behavior. And for mounting the microphones, we tried a couple of different types of mounts. The first type we tried was this more rigid silicone muzzle. And this one looked pretty promising because it was pretty sturdy. You can attach it to the head of the dog, and there was a nice spot here in the back of the head where we could attach the IMU. And then the microphone can be attached here along the muzzle here. And so in that respect, it worked pretty good. Like it was a pretty stable structure. Unfortunately, the problem with this one was that you can see that the muzzle, the silicone part, it kind of protrudes from the front of the dog's nose. And this turned out to be, when we tried it out, it was very problematic because when a dog's, when it's searching for scent, sometimes it would bring its nose really close to the floor. And in this case, what happened is that it would scrape the silicone area. And what you end up picking up with the microphone is that you just end up picking up this scraping noise, and it was not very useful. So after that one, we tried a different one. So in this second picture, there's like a soft fabric muzzle. So this one turned out to be much better. Sorry about that. This one turned out to be much better. And one, it was much more comfortable for the subject, for the dog. And then 2, the main important thing was that it did not protrude from the nose. So the dog could like freely sniff, and then we wouldn't have those, the background, the noise from the scraping, essentially. But with either case, it actually takes some time for the dog to acclimate to it. It's kind of like essentially they're kind of like wearing a mask, right? So we're all used to wearing masks these days, and it's not the most comfortable thing to do. With a muzzle, it's like a couple times more uncomfortable, since it's more rigid. So comfort was a really big factor, and then this other factor was, of course, it doesn't get in the way of the search. For placement of the equipment, here we have a drawing of the dog. And then on the table, we have a laptop. And what we did was we mounted the mic on a soft fabric. We used some clips and just clipped it on. It worked pretty well. And so you will have the mic there that's aimed towards the nostrils of the dog. And then the transmitter was placed on the vest. So dogs are very, it's very common for a dog to wear a vest. So that part didn't require too much acclimating for the dog. So there was a lot of space to put the transmitter. That was pretty easy. And then the receiver, of course, is on the table next to the laptop so that it can receive the audio data and then send it over to laptop. And this was transmitted through UHF. And then the IMUs, one was placed here by the muzzle, and then the other one was on the back of the dog. So that's it for the sensor placement. Here's the final picture of the, I guess the picture of the final prototype. We have the soft fabric muzzle, the transmitter, the receiver, and then it has, it uses audio jack that goes to a laptop. And then we have the 2 MetaMotion C sensors. And here's Stormy, our Nosework dog. And yeah, it turned out pretty nice. So for the audio data we collected, we had 20 minutes worth of audio recording. And from this, we broke it down into 170, we segmented into 171 different samples. And we labeled each of these samples. 54 of them were sniffing audio, I guess. Yeah, so the audios were labeled as sniffing, and then 69 of them were, it was like panting, where the dog was panting, and then 48 was where it was no background noise. So with the model, what we did for the training data was we split this into 137 for the training, 16 samples for the validation, and then we saved 18 for the final testing. And for pre-processing of the audio, what we did was we ran a short time Fourier transform to get the, I guess, the frequency domain version of the audio. And we'll show you a picture of that afterwards. It's pretty clear. Like you can see a difference in the picture for the of the short time Fourier transform for sniffing data, say, versus panting data. And so, yeah, what we have is that the sniffing data would look like the other sniffing data. And after that, what we have was we trained a neural network, and this neural network would classify between either the dog is sniffing or it's not sniffing. So it's a pretty simple classifier. In this case, we just want to distinguish whether or not we can actually tell a difference between a sniffing audio and non-sniffing. In the future, we might want to be able to also tell the difference of like how frequent the sniffing is, because when the dog is just introduced into a room, is trying to detect an odor, its sniffing pattern is different than when it actually finds the odor scent. So when it's in odor, it'll start sniffing faster. And then when it's at source, then also the speed of the sniffing also changes. So in the future, we'll probably try and make it a little bit more complicated so that we can tell the difference between those different scenarios. So for what we have currently, sniffing versus non-sniffing, our final accuracy on the test data was 94.4%. And I'm not sure if this audio worked here, but we'll test it out. I'm not sure if you guys can hear it. But in either case, it's, I think we have we have video afterwards. You can hear some of the sounds. But the main part of this is that here's the STFT, the short time Fourier transform of the audio. And in the x-axis, you have the time. The y-axis is the frequency. And the color is like the intensity. So if you look at the sniffing, the panting data, you can see it's a little bit more dispersed. In time, the intensity is not as high. There's more frequencies, and at least the time one kind of makes sense, right? The panting sounds are usually when a dog pants, it's usually the duration takes a little bit longer than say a quick, like a sniffing sound. A sniffing, you expect like a short duration, and then maybe like in this case we find that it's more even the frequencies are more focused. So basically, we want to be able to have a classifier that will be able to tell the difference between data that is here versus data that is over there. So panting versus the sniffing data, or sniffing versus non-sniffing, essentially. So for that was the audio part. For the IMUs, what we have is we took the video, we took the IMU data and we looked through, went through each individual part of the video and we labeled parts. They're either lying down, sitting, standing, walking, or some of the other labels. There's the sponging that we saw earlier. And then the don't use label here is just when in the video we couldn't really tell because maybe the dog was like blocked by an obstacle or for some other reason, so we just marked those as don't use. Finally, we have like maybe 234 total events labeled. And so, you might have, if you want to visualize it, it would be like sitting would be something like this, lying down, they're standing, and while they're sniffing while they're falling, looking for the odor. And then here's the sponging where they're elevated. And so for this one, we because of time constraints, the semester ended. We didn't really have time to get to the point where we trained a model for detecting a model for classifying the activity based on the IMUs. So that will be done for a future, for the future project. And here we have finally we have a recording of one of the sessions we had. There's Dr. Jackson. There's Stormy. And you have the IMU labels of IMU data on the bottom. So I think if I heard clearly, I think there was you can hear that the sniffing sounds at this part when it's in odor or at source. When it's at source, it's a much faster rate for the sniffing. Let me close this so we don't go to advertisements. Okay, so I think that's concludes our presentation. So if there's any questions, please feel free to ask.